It's part 3 of the TACO presentation, The Evolution of Radiant Mixing. I'm John Barba, and so far in this program we've learned about the need for mixing with radiant systems and about the mixing valves available. We've also learned in depth about the most basic mixing option available, the three-way tempering valve, and we've also learned about the limitations imposed by the concept known as CV, the pressure drop rating of a particular valve. Now in part 3, we'll take a look at some of the motorized mixing options, in particular the TACO I-valve. TACO offers a motorized three-way valve option called the I-valve. The I-valve is available in either a set point model or a reset model. In this segment, we're going to take a look at the set point version. This electronic motorized valve offers a fixed radiant supply water temperature, just like the three-way tempering valve does, but it does so with a three-way ball valve with an intelligent control motor for much more accurate and much more responsive control when compared to the three-way tempering valve. The I-valve is also low voltage and should be powered directly through a 24-volt transformer. The I-valve is also easily adjustable. Simply move the dial on the motor to the temperature that you want, and the valve will take care of the rest. What's more, the valve has a built-in boiler protection function. A sensor is installed on the boiler return leg as close to the boiler as possible, and if the boiler return water temperature starts approaching a preset minimum, the I-valve will start to close, thereby directing more boiler water through the bypass back to the boiler to prevent flue gas condensation. The I-valve will minimize flue gas condensation, especially during startup, especially when compared to a three-way tempering valve. The tempering valve arrangement will merely minimize flue gas condensation. The I-valve in the set point version is available in 2-, 3-, and 4-way configurations. All of them do the same job, but they do require slightly different piping arrangements. Earlier we showed you a three-way tempering valve piping arrangement, and we showed how the CV rating of that valve could create issues with circulator sizing. The I-valve has an even lower CV rating than the three-way tempering valve. It has a CV of 3 compared to 3.8 for the tempering valve. Now that would create even more pressure drop issues on the system. Despite that, however, the I-valve can be useful when piped in a primary-secondary fashion, although like the tempering valve, it is best suited for smaller jobs around 4 gallons per minute or so. The key with any primary-secondary piping arrangement as shown here is the spacing between the supply tee and the return tee on the primary loop. That spacing should be no more than 6 inches or 4 pipe diameters. It's important to note that the radiant circulator will need to overcome the head loss through the radiant tubing, the small amount of head loss through the hard piping on the secondary side, and the head loss through the I-valve itself. Wiring up the I-valve is pretty simple. The I-valve will come with 2 sensors, a radiant system supply sensor that's strapped onto the radiant supply pipe after the circulator, and a boiler return sensor. This sensor is strapped on the boiler return piping as close to the boiler as possible to sense the boiler return water temperature. This sensor is only needed if you're using a cast iron boiler and would like to use the I-valve to automatically protect the boiler from low return water temperatures and flue gas condensation. You don't need this sensor if you're using a modulating condensing boiler and aren't worried about the low return water temperatures. All of the sensors are wired up as shown, with one leg going to the COM terminal and the other leg going to the appropriate S terminals. The boiler return sensor would be wired into terminal 3 and the radiant supply sensor wired into terminal 2. The I-valve is 24 volt and it may be wired as shown in conjunction with a 24 volt transformer with an external N switch. If it's serving a multi-zone radiant system, then the I-valve should be direct wired to the transformer and powered continuously. Programming the I-valve for set point's also easy. All you have to do is adjust the dial on the top of the controller to the desired radiant supply water temperature and let the valve take care of the rest. Operation of the I-valve is pretty simple to understand. The radiant supply sensor will tell the I-valve the current radiant water temperature. The valve will then compare that temperature to the desired temperature programmed in at the dial. If the radiant water temperature is too low, the I-valve will open, allowing hot boiler water to mix with some of the cooler radiant return water. The rest of the radiant return water will head back to the primary loop. The valve will allow the radiant supply temperature to increase gradually until it finally reaches the desired set point. Now, when the radiant water starts to cool down, the whole cycle starts over again, and the valve will open and the mixing will continue. The set point I-valve also protects the boiler. No additional programming is required here. When the sensor is installed and wired to the unit, the I-valve will automatically protect the boiler from return water temperatures any lower than 135 degrees. When piped in a primary-secondary manner, the secondary or radiant circulator would not need to be sized to overcome the head loss of all of the piping all the way back to the boiler. It would only have to overcome the head loss in the secondary itself. However, in a system larger than, say, 4 gallons per minute, the CV of the I valve would be such that the overall pressure loss in the system would require a larger 00 series circulator, such as a 0011 or a 0013. A smaller system, on the other hand, would be ideal for the I valve, and that's what we're about to take a look at. In this example, let's use a 15,000 BTU radiant system designed to a 10-degree delta T. If we were to math that out using the universal hydronics formula, we would find that it has a flow rate of 3 gallons per minute. And let's say the radiant tubing head loss was calculated out to be 4 feet, and that there's an additional 10 feet of hard piping in the secondary circuit. That would total out to be about 6/10 of a foot ahead. 10 foot of hard piping times 1.5 to allow for the fittings would be 15 feet. 15 times 0.04 would be 6/10 of a foot ahead. Again, put it together, that's 4.6 feet of head. The valve head loss, with 3 gallons per minute flowing through the I valve with a CV of 3, would total out to 2.31 feet of head. Again, the GPM of 3 divided by the CV of 3, 3 divided by 3 is 1, 1 squared is 1. 1 times 2.31 would equal 2.31 feet of head. We put that all together on the secondary side for the secondary circulator, we'd have 6.91 feet of head. Let's take a look at a TACO pump curve chart and plot that out. At a flow rate of 3 gallons per minute, just under 7 feet of head, we would find that that circulator would need to be a TACO 007, or a 008 would work as well. Well, that's all for Part 3 of the evolution of radiant mixing. Thanks for joining in. In Part 4, we'll take a look at the benefits of outdoor reset and how easy outdoor reset can be with the I valve. We'll see you next time.